Hello everybody, this is Mr. Ainsworth and we are in MRWC. We're talking about math, reasoning with connections here. And we're going to do a little prep for 1B1. Okay, so it's a little prep. When I say prep, I mean a discussion. Some of you guys might be familiar with the term fluency moment, but this is basically a prep. Okay, so I'm going to put prep right here, which is short for prepare. You guys for your activity 1B1, which happens to be following right here. And that's what's going to happen once we're done. Now, if you're at home, well, this is a video and you're watching it at home, just pause and play, go at your own speed. If I go too fast, this may be new to you, so pausing and playing and re-listening to it is always a good idea. So take advantage of the fact that it's a video where I'm helping you out. Okay, so we are going to get into a topic through the next few sections here, all the way basically in the first semester from sections 1 through 5, on a theme of called closure. Okay, this is the major overwhelming theme, closure, and we're going to get an idea of what it means to be closed under a certain operation. So let's talk about a little language of mathematics first. Okay, a set is closed. Okay, notice the keyword closed under a given operation. Okay, it could be multiplication, it could be division, it could be adding, it could be subtracting, it could be square rooting, it could be squaring, it could be any operation. So under the operation that's given, and it will specify in the problem here, whatever we're dealing with. So we say a set is closed under a given operation, no matter what it is, if performance of that operation on members of the set always produces a member of the same set. Okay, if it produces a number in the same set under that operation, it's closed. Okay, if it's not, then we say it's not closed. Okay, a little caveat right here. We do not, all right, we do not use the term open. So if a set is not closed, we say not closed. We do not say open. So the whole idea of this little discussion here is to get used to what it means to be closed under a particular operation, given a particular set. And we're going to start off with finite sets. Okay, you have to get used to the word called finite. Okay, a finite means a specific number of elements within that set, which in this case, like in the first example here, set S only comprises of three numbers, -1, 0, and 1. We can call them numbers, elements, okay, something in the set here. And we want to show that it's closed under, or determine if it's closed under multiplication. So multiplication is the operation. Okay, and the numbers in the set, or the elements in the set, this finite set, finite is a number that's not infinite. Okay, it's a specific number. You know, it happens to be 3. So what we want to do is come up with a way to diagram this and show that if you take any two numbers in the set, multiply them together, you get a number in the set. That's what it means to be closed. If you take any two members in the set, operate on them under the given operation, in this case it's multiplication, and you perform that operation on the two members, if you get a number that's produced and it's in the same set, in this set S here, if it's -1, 0, 1, then we say it's closed. And the first thing that people do to determine this is to list all possibilities. Okay, this is your first basic method. Okay, in fact, let's write that down. So list, okay, all possibilities. Now this is possible if the number of possibilities is finite, meaning countable. If you can actually do it. If you have an infinite set, then doing this is not possible, and so you have to have another way of doing things. But in this case, since we're only dealing with a finite number of elements, we're talking about 3 numbers here in the set. It's going to be easy. So let's list all possibilities. So here we go. We're going to take any two numbers in here, even with itself, a number with itself, multiply them together, and if the result is in the set, we're going to say it's closed. And to show that it's closed, or determine if it's closed, because we're supposed to determine this, it doesn't say show, it says is it closed, and then you have to list them. So here we go. Let's start off with 0, for example. So if I take 0, one of the numbers in there, and I multiply it by every other number, including itself, what do we get? So 0 times 1, well that's not 1, that's 0. Come on, Ainsworth. Okay, 0. 0 times anything is 0. 0 times -1, that's still 0. And 0 times itself is 0. So notice that I start off with 0. and I multiply it by every other number in there, including itself. And then I take negative 1 and I do the same thing. So negative 1 times 0 is 0. Negative 1 times 1 is equal to negative 1, and that's in the set. And then negative 1 times itself, well, that's just 1, and that's in the set. So far, the results, which I'm going to highlight here, anytime we multiply two numbers in the set, we get a number or a result that's in the set. Okay, and then speaking of that, let's talk about symbols here. We have a symbol called element of. Okay, it's the funny looking E here, and that means element of. That means it's inside the set. Okay, now if it's not in the set, we slash it. You put a slash through it, and so what that means, it means not an element of, which simply means it's not in the set. So not element of means not in the set. That's all it means. So make sure you write that down when we're off to the side. Okay, because I use symbols in mathematics all the time because it speeds things up. Now 0 is in the set, so it's an element of S. So over here 0 isn't, still it's in the set, it's an element of S. Negative 1 is an element of S, and 1 is an element of S. All the results so far are in the set. So far I was able to show that if you take any two numbers in the set, multiply them together, the result's in the set. But I'm not done yet because I did it for 0, I did it for negative 1, and now I have to do it for 1. So here we go. So 1 times all of these numbers. So 1 times 0 is 0, that's in the set. 1 times 1 is 1, that's in the set. 1 times negative 1 is negative 1. So all of these numbers, these results are in S. Okay, they're inside S. They're a part of S. Okay, they're an element in S is what I'm saying. And since all the results that I've highlighted, okay, are in the set S, that means the set is closed. Because I didn't multiply something and get a number outside the set. Anytime I multiply two numbers that are from the set, I get a result that's in the set, which means it's closed. So right now, what I can say from this, so here's my conclusion right now. In fact, let's write that down. So conclusion. Okay. Since the product, okay, since the product of any two numbers in the set, okay, since the product of any two numbers in the set results in a number in the set, okay, since the product of any two numbers, well, I can just make it more simple, is in the set. Since the product, okay, that means you multiply them together, of any two numbers is in the set. So let me insert that word, is in the set, okay, comma, set S is closed. Under multiplication. Now you always have to specify the operation because the question will change if I change the operation. Okay, this is called the conclusion. Since the product of any two numbers is in the set, set S is closed under multiplication. Now that may not be true for addition or division or subtraction or squaring or any other operation. All right, so what you have to do is you have to list them. So the first method of figuring out the idea of closure is simply by listing. Okay, now there are other ways to do it. Okay, you do not have to list. You could also diagram it too. So let me, instead of listing, let's show an alternate way just for funsies right now. Okay, so another way, okay, is to diagram it. So the question is, how can you diagram this? How can you show it in another way, showing all of these 9 possibilities? These are 9 possibilities here. 1, 2, 3, 1, 2, 3, 1, 2, 3. There's 9 possible outcomes. Or possibilities here. Possibilities, I should say. So 9 possible ways to multiply. How do you show this in a diagram? So let's go off to the side and take a look at that. And believe it or not, we do it the exact same way you were taught back in grade school. okay, what we're going to do is make something kind of looking like your times tables, okay? But we're not going to do a 12 by 12. We're going to put a times symbol here because we're multiplying. And we're going to put, instead of put the numbers 1 through 12 like you did in grade school, we're going to put the elements of the set. All right, -1, 0, and 1, -1, 0, and 1. And then what we're going to do is we're going to fill out the table by multiplying, because our operation is multiplication. That's the operation. Okay, so remember that. Okay, so what we're going to do is we're going to multiply and fill out the grid. So here you go. Right here in the first, let me see. Let me use some colors here. So right here in our first cell right here, we take -1 times -1. Okay, what do you get? Well, you get 1. And then you move from left to right. -1 times 0 is 0. -1 times 1 is -1. All right. There are 9 outcomes, as I was saying. So you have to fill in the blanks here, and you got to multiply every possible combination of numbers. All right. And then on the second row, 0 times -1 is 0. 0 times 0 is 0. 0 times anything is 0. So the second row should all be zeros. And then on the third row, you multiply by 1. 1 times -1 is -1. 1 times 0 is 0. And then 1 times 1 is 1. And if you count them up, there are 9 possibilities. Okay, there are 9. And notice all of these numbers are in S. Okay, all of them. All the results are in S. And because of that, it's closed. That's the whole idea of closure. And I'm spending a lot of time right now going through it because it's going to get a lot more complicated as we go on. All right, and so if we thoroughly understand what's going on now, well, then the harder stuff later on when we get to more complicated number sets is a lot more understandable. Now, to truly understand what's going on, you have to figure out when things are not closed too, because it's not always closed under a particular operation. So notice that on this one here, I'm going to switch the operation, okay? And the operation is going to change to addition, from multiplication to addition. Same set, but the operation's changed. So the question 2, okay, this is Q2, is the same set, -1, 0, and 1, closed under addition. That means if you add any two up, is the result in the set. Okay, that's the question. So Q for question is if, okay, you add any two numbers in the set, is the result in the set. Is the result in the set? That's the question. And if you can answer that question, then you can answer, you know the answer. Okay? Now, we could list all 9 possible ways, but instead of multiplying, we add. All right? But in this case, it's going to be really easily seen that if you take 1 plus itself, you get a different number that's not in the set. And so if I can find any possible combination of two numbers that if I add them together, okay, again, we're adding now, all right, and then the result is not in the set, then it's not closed. And that, my friends, is called a counterexample. Okay? So in this case, if I take 1 and add it to itself, 1 plus 1, I get 2, and 2 is not in the set. And this, my friends, is a counterexample. So I'm going to say no right here, all right, because, all right, 1 plus 1 is equal to 2, and it's not in S. 2 is not a number in there. Okay, 2 is not inside the set. And that's a fancy way of saying, when I say not an element of S, I'm saying it's not in the set. Obviously, it's not. Only -1, 0, and 1 is. Okay, so this is called a counterexample. So let's write that fancy word down because you're going to need to get familiar with this. Counterexample. All right, and it only takes 1 to prove something wrong. So let's make a little note of that. All right, it only takes 1 counterexample to show something that is false, to show something false. Let's highlight that. Okay. Now there could be more than one counterexample, and sometimes with infinite sets, there's an infinite number of counterexamples to show something that's false. But in reality here, anytime that something's false, all you have to do is come up with 1. Okay, it only takes one counterexample to show something false. Remember that. Okay, so not all sets are closed under a particular operation. This set is not closed under addition. Oh, let me make a note of that. Okay, so conclusion. All right, not closed. Okay, under addition. Because we showed that 1 plus 1 is 2 and 2 is not in the set. It's as simple as that. So in the beginning here, it sounds kind of trivial, but this is actually a very, very important concept in number theory, as you will see in the first 5 sections of MRWC. Okay, now let's change it up a little bit, just so you can really try to get a better understanding of what's going on. If we take 2 and add it into the set, and so instead of having 3 members, it has 4 members in the set, will it still be closed? I don't know. Let's find out. So let's put 2 in the set. So now we have a new set. Okay, what does it look like? Now S is looking like 2, -1, 0, and 1. So now that's our new set, because we put 2 in the set and says, will it still be closed? Okay, and we're going to have to make an assumption here because I didn't state the operation. We're going to under multiplication. Okay, so let me make a little note there. Under multiplication, not addition. I should have been more specific. Okay, under multiplication. So there's our operation. So if you multiply any 2 numbers in there, will the result be in the set? Okay, and if I test it, let's see what goes on. If I take 2 times 1, I get 2. Okay, and that's in the set. So far it's looking good. All right. 0 times 1 is 1, and that's in the set. So that's still looking good. All right, -1 times 1 is -1, and that's in the set. So it's looking like it's closed, right? All right, but if I take 2 times -1, I get -2, and that's not in the set. Okay, so it's not closed. Okay, does that make sense to you guys? It's not closed because I came up with a counterexample right here. It's called a counterexample. Okay? So anytime you can come up with one that shows it's false, it's going to be not closed. If you can't find a counterexample, then it's probably going to be closed. And then you'll have to later on prove it. And that's a different thing. We'll get to that later. Okay? Now number 2, is there any number that can be included in the set and still retain closure? All right, is there any number that you can include in the set and still retain closure? Like if I just came up with a number, say let x be that number. Okay, so put x in the set, let's say. Okay, x in the set. Let x be any other number. Any other number, let's call that x. Okay, so now s looks like this. X, whatever that is, -1, -1, 0, and 1. So now we still have 4 members, just like the previous one. In the previous example was 2, but now it can be anything. It can be 5, it could be 10, it could be -9. I don't care what x is. It's just a number in there. All right, will this be closed? Will it retain closure? Okay, under multiplication, that is. All right, so we're gonna have to assume. Let's see. We have to write down the operation. So under multiplication. We could specify addition, but let's specify operation. I mean multiplication as our operation. Okay, so let's test. Okay. So let's start multiplying here. Okay, so it looks like 0 times x is 0, which is in the set, so looking good so far. All right, let's take x times 1. X times 1 is x, which is in the set, looking good there. But if I take x times -1, all right, I get -x, which is not in the set. All right, so right away, boom, it doesn't matter what number I put in there. If I add another number, all right, it's not going to be closed. Does that make sense, you guys? Okay. Okay. And I'll tell you what, I'm not going to worry about 3, so we're going to skip this one here for right now. Let's see, I do want to read this though. So let's read this. Let's read the last class discussion here. So under what circumstance would a set be not closed? Okay, not closed. What is an example of a set that is not closed under a certain operation? Under what circumstances would a set be not closed? Okay, what is an example set that is not closed? Okay, so if it's not closed, okay, if the result of the operation of two elements under the operation is not in the set, all right, then it is not closed. So this is basically just kind of like a summary question here. Like, when is it not closed? That's the idea. All right, so if a result, let's write it out. So if a result, okay, under any operation, I don't care what operation you pick. So it doesn't matter whether it's, adding, subtracting, dividing, multiplying, square rooting, squaring, okay, I don't care what the operation is. If the result now, okay, so underline that word, if the result under any operation is not in the set, is not, okay, in the set in question, okay, then all you have to do is say the set is not closed, all right? So the conclusion here is that then the set in question, whatever that set is not closed. And remember, we don't say open, okay? We just say not closed. So that's the key. All right, and so what is an example? Okay, well, here's a simple set. Let's take a set with 2 numbers in it, 0 and 1. Okay, I'm going to say that this set is not closed under addition, okay? I'm going to make a statement here. S is not closed under addition. Why? Because if I take, I need to show a counterexample of that, right? So if something's not closed, I have to come up with at least one counterexample to prove that it's false. And it's easy in this case. 1 plus 1 is 2, and 2 is not in the set. 1 plus 1 equals 2, which is not an S, and that means it's not closed. So this is your first exposure probably to closure, and that's why I was going in this depth, because this is new and it's going to take a while to get used to. Okay, so what I would suggest you guys do is that if you want to rewind and listen to any part of this again, because it's new and a little bit abstract in the beginning until you get used to it, rewind the video. I mean, that's the advantage of these things. So use it to your advantage. Get through this here, go slow at your own pace, and then I will see you in the next activity in 1B1 when we talk about closure again. Okay? I'm Mr. Ainsworth here at Great Oak High School in the Temecula Valley District here, working in MRWC, and I look forward to seeing you guys in my next lesson. Take care. Bye-bye.